Hello students, welcome back. Let us now begin section 3 of this notebook, Inverse Matrices. What is an inverse matrix, by the way? Let's review that. And this is the definition we used in Module 3. Did I say definition? Excuse me, I take it back. It's a naive description, not a definition. And we're going to come back with a bit more precise treatment in subsection 3.4, but that's going to be in a separate video. Anyway, let's come back to a review. A matrix A inverse, yes, we read it, A inverse, not A to the negative first power. This matrix is called the inverse matrix of A if it satisfies this algebraic rules. A inverse is equal to A inverse A, and that is equal to I, the identity. If such a matrix exists, we'll say A is invertible, and the matrix inversion satisfies a number of rules, but here are a couple. Actually, I took two of the most important. Both are important, but this one's really important. AB inverse is equal to B inverse, A inverse. We have to switch the order of multiplication, and multiplication are not commutative. Okay, so much for the review, and let's go to the next topic, elementary row operations. To a certain degree, this is a review too, because we talked about elementary operations in previous section of this notebook. But that's first for an application on solving a system of linear equations. This time we're going to come back and discuss that in terms of a little bit more theoretical point of view. Just a little reminder what we did. We started off with this kind of thing, a system of linear equations, and then we expressed it in terms of matrix multiplication form. AX is equal to C form. And then we applied a bunch of algebraic manipulation and a bunch of elementary row operations. And in the end, we ended up with a little bit simpler matrix, which helped us solving the equation. The characteristic of this simpler matrix is this lower left-hand side corner. These are all zeros. Below the principal diagonal, all zeros. And these kind of matrices are called row-reduced echelon matrix, but I'm not going to go too deeply into that. And sometimes we can reduce it even further, and then not just these zeros, but create some other zeros as well, and then we end up with some identity matrix or something very close to it, embedded in which case, of course, the solution is even easier if we actually accomplish it. That's where we are headed, as a matter of fact, in this section. Anyway, that was a quick review of the use of elementary row operations. Now let's discuss the same thing in terms of a little bit more theoretical viewpoint, in terms of matrix multiplication. This is a starting point. Multiply an identity matrix, consequently, no change. Next, multiply a non-zero number to a certain row. Okay, this is an elementary row operation. And how is it related to identity matrix? Well, here we go. First example, start from identity and change this 1 in the second row into 3. And what does it do? Multiply 3 to entire second row. What if we take the fourth row and then multiply fourth row and replace this one by 1/2. That's equivalent to multiplying 1/2 to entire fourth row, as you can see here. So the conclusion. The elementary row operation is equivalent to multiplying some clever matrix, elementary row operation matrices, on the left. And those matrices are kind of variations from identity. How about the next example? Adding one row to the other. Okay, here are a couple of examples, and let's look at the first one here. Adding blue row, third row, to the second row. So starting from 1 here, and then move it up to the second row, and then insert this 1. And this doesn't change because I don't want to do anything. I don't want to change this third row. The change takes place in the second row here. You see, I want to add like this. So both ones are in the second row. This one was there before, red one. The blue one came from the third, so vertically it went up. How about this one? Adding second row to the fourth row, so start from this second row, and vertically it comes down to fourth row, but this one stays as 1. Anyway, the conclusion. Elementary row operation corresponds to multiplying some matrix to the left. Here's a third example, changing 2 rows. From the first row, we're coming down to the third row. And third row, we are going up to the first row. So this one came down, this one went up. But we are leaving the previous row, so these became 0. Anyway, same conclusion. Elementary row operation means multiplying something to the left. That's a conclusion. So how do we use it for the system of linear equations? Here is a theoretical background here. We begin with AX equals to C form, as you saw, like this. Excuse me. AX equals to C, okay? And then apply elementary row operations, E1, and then E2, and then E3, E4, E5, all the way to ER. Consequently, we get this matrix, which is a little bit simpler than previous one. Hopefully, very, very simple row-reduced echelon matrix. And then if we do the same thing to the right-hand side of the equality, we get a little bit different non-homogeneous part, but in any case, we can solve for x. It depends heavily upon how simple this matrix is. Now, what we want is this matrix becoming really simple. So simple that it becomes identity itself. That's the most ideal, and that's what we want to focus upon. So we are not going to consider the linear equations anymore, even though it's related. We start from matrix A, which we'll call A0, and then apply E1, and that becomes A1. Apply E2, apply E3, apply E4, all the way up to apply ER, so we end up with multiplying these matrices E1 through ER to the left. And let's suppose that the resulting matrix is not just row-reduced echelon matrix, but something even simpler, very simplest type. The simplest type of row-reduced echelon matrix, which is identity. If so, if that's possible, then this is the inverse matrix. You see, A inverse times A is equal to I. The key is, how do you find this? And the key is right down here. We consider a parallel computation. We start from I instead of A, but apply the same elementary row operations. Apply E1, apply E2, E3, E4, all the way up to ER. The same as before, which generated I. But then again, this time I started from I. Identity doesn't change anything. So the result is nothing more than just E1, E2, E3, all the way up to ER to the left. And that is the inverse matrix. You see, the same thing times A equals to I. So that is the inverse matrix. That is the theoretical background. What we're going to do now is just set up two matrices, A and I, one blue, one red, and then apply the same operation. And when original matrix, blue matrix, becomes identity I, then the parallel computation will yield the inverse matrix. Ready for an example? Okay, let's do that in the next video.